Today we have Andrew Doroshenko, mechanical engineer with Lockheed Martin.
I'm Andrew Doroshenko from Lockheed Martin here in Bothell, Washington. We have got a couple other folks on the line from my site today, Evan and Ratnanjali. If you have anything to add, just feel free to throw it out there. I don't really have a ton of slides to go over here. Just kind of want to do a brief overview of what we do at Lockheed, as well as what I do specifically, and then some suggestions I have for general STEM activities. This is run by the STEM Council. We have a little STEM Council here at our site that does outreach to different schools and to I guess TAF as well for different events virtually, and so this is our part of that. So a little bit about me. I grew up in New Jersey. I always thought I wanted to be a airplane designer since I was a kid. My dad would make me like paper airplanes and help me with really intricate paper airplane designs, and then I would modify them to do different things, and I just kind of set on that engineering mindset. Started out with Legos and building and design type of activities they're stimulating, right? So I did science fairs, home projects, extracurriculars like a robotics club at my high school, as well as in college. I did extracurriculars that were engineering based, really, to give me experience and improve my chances at college and job. I also do RC airplane building. I haven't done that in a little while, but I was big into that coming out of college since I was a team lead for my aero design club there. So on the bottom right here, you can see a picture of my giant scale RC plane taking up most of the garage, made of balsa and plywood here. Very relaxing experience. And you can apply engineering as well while also doing sort of more like trade arts and crafts. So I enjoyed that. Yep, top right is also being a mechanical engineer helps with various other activities like fixing your vehicle. So I have an old Bronco here I'm working on getting fixed up. So what we do here, I'll just go in a little bit more. What I do specifically, I have been involved in a lot of different engineering disciplines at my site. We are essentially a prototyping shop, which is kind of what you see here in this Big Bang Theory screenshot, where in a prototyping lab, it's very fast paced. You're innovating on the fly, creating ideas to solve problems, trying it out, and then trying new things. So I've kind of gotten the opportunity to get my hands in a lot of different aspects of what we do, including heat transfer analysis, computational fluid dynamics, structural mechanics. So that's actually, does something break when you apply loads? Mechanical design, so I use Creo and do CAD work and design mechanical parts, make drawings for them, and an important part of that is geometric dimensioning and tolerancing. So will the parts actually fit together? Something that's not really taught in school or even university, from my experience. Part inspection, so actually getting hands-on. I actually get into the lab, I inspect parts as they come in, assemble components, see if they work, and then if they don't, go order more parts and try it again. So I'm kind of just like I haven't watched Big Bang Theory in a while, but the one actual mechanical engineer from that show that's kind of tinkering in the lab. That's kind of what I do. And an important aspect that often gets missed from what engineers do is that we have to be extremely social. We have to collaborate a lot and communicate a lot with our team, with the customer, with program managers that don't have as much technical background. So it's really important that we actually collaborate a lot in a team environment. I really think that any engineering degree or science learning is it's not really complete without doing some team activities without being involved in a team. You can't just be book smart. You also have to have some, social skills, I guess. So that's definitely critical. Let's see. Yes. So some examples down here are kind of interesting. On the bottom left is like a typical hand calculation for convection heat transfer. So cooling a computer chip by a heat sink, metal heat sink with lots of fins on it. Actually sizing that, you can do that with some basic hand calculations. And then on the bottom right here is a picture of a CFD simulation. So air, I guess, going into a radiator, not exactly sure, but you can simulate the way liquids flow through components and how heat's transferred and what happens with pressure drop and all those things. That's something that we have to do as well as part of the whole cooling design process. And in the middle is just a screenshot of some Creo mechanisms. So do a lot of that. So overview, a little bit more about my company. Not too much about this, but Lockheed Martin, if you've been to an aerospace museum, you've heard of Lockheed Martin. We have a lot of planes in there, from F-22 to, SR-71, Blackbird, we have 4 different divisions. We're a huge company with aeronautics division, missiles and fire control, rotary and mission systems, and space. So you can get a pretty good idea for what each of these divisions does just by their name. I'm part of the rotary and mission systems. So what we do is more the mission systems side. So getting into, so getting more into that. Next, at my site specifically, we work on directed energy, which is new technology. It's been around for a little while, but not in the same form. In the past, we've had airborne weapon system. I think it was a 747 with a giant chemical laser on it. But there's a lot of problems with that. And I think that the project eventually got canned. But now, with the dawn of electric lasers, there's a lot more possibilities. And so this technology has been growing and scaling up, and I like to consider it sort of golden age of directed energy, because there's so much development at such a rapid pace and a lot of competition. So that's exciting. So on the left here, you can see Army, and then bottom right is Navy, and then upper right, Air Force. So we've got all branches of the military interested in directed energy, putting a high power laser on a platform and using it to defend against incoming missiles or shoot down ICBMs, stuff like that. That's the goal here. So really, it's defense here. And you can kind of see a little drone or something here being shot by this animation right there. But yeah, so great pictures. Little bit more general here. Getting into what I like to more or less convey to students during these STEM activities is the process for design. Well, first there's getting them interested in doing these projects, and then actually implementing it would follow this process. So it's pretty generic. I mean, you've probably seen it before. Ask what is the problem, and then start brainstorming solutions. Plan out, spotlight video. Plan out how to solve the problem. So planning, it looks like a small step right here, but planning is everything. So that involves creating drawings, creating designs, having design reviews, all of that. Creating the actual project or product. So that's actually building it. If you did your planning right, then your creation step will be a lot easier. So emphasis on the planning. And then testing and improving, that's the fun part. So whenever whenever we get into that stage of the STEM activity, it's, that's where everybody's smiling, having the most fun, and hopefully being motivated. And then after that is sharing, and essentially telling people about your successes, and then maybe being able to do something else or interesting. And also debriefing and learning from mistakes and whatever happened along the way. So on the right here, I added a few sub-steps on each of these generic steps of the design and engineering process. So in industry, during the ask and imagine phase, you would have a request for proposal. You have a customer with a specific need comes to you, hey, we need to, put a giant laser on a ship or whatever, So, okay, well, let's see can we do that? And then we would consider whether we want to make that, if that'll be profitable for us, and then maybe move forward with creating a proposal and being part of the bid. So, so there in the classroom, it might be, you give a student like a couple of choices, or create a solution to this problem, and then you'd brainstorm different creative out of the box ways of solving that problem. And then if you get the bid, then get the contract, then you start the planning phase. So this is really where there's all the work happens during this planning phase. That is all the engineering work, and where the entire team is engaged. So you start with requirements. What does your customer really want? And there's a lot of interesting, I guess, takes on requirements and how requirements can be flowed down wrong. A lot can go wrong in this step, where if the customer doesn't specify exactly what they want, you could give them something that's not actually as useful for them. Or with scope creep, they change what they want, and then eventually it changes into a completely different product that isn't really what they needed in the first place. So it's really important to communicate with the customer what exactly do they want in terms of requirements, and what kind of a product do they want, and then trying to stick with it, so that you don't have sort of suboptimal product for what you originally started out with. So let's see, and then trade studies. So trade studies happen throughout the design process, continually looking at different ways of solving problems. You can create completely different conceptual designs. You can have different subcomponents, or even just different adhesives for certain applications within your product that you have to do trade studies on. So there's a lot of sort of taking it slow, making sure you make the right choices, and have educated decisions for each of your design decisions. So a big step that I only really learned once I was in industry, actually practicing for a while, is the different design reviews, reviewing with your team along the way. The main ones are conceptual, preliminary, and critical design. So conceptual is you have a general concept, you're very early in the process, and you can make big changes easily in the conceptual design phase. You really want to make sure that you have a overall package size for your product that you think will work and you can work within. Then you work into the preliminary phase, where you start getting more detailed, and then at the critical design, once you pass the critical design, then you actually can start buying things, because you did the full detail design and you are very confident that your design will work. So those are essentially just steps, or gates to actually start ordering things. Yeah, and all within the planning stage is design, like the CAD stuff I was talking about, analysis, making, convincing yourself and your customer that your design will actually work. A lot of collaboration going on, a lot of planning. That's kind of redundant, but planning involves like looking at the schedule, making sure that when you order things, things come in on time, and work with your schedule. Working with procurement and your entire team, making sure you have resources or people available to help you along the way. So yeah, that is all for the design phase. Hopefully this is useful to everyone. Sort of a just general overview of this design process. I'll keep going through this this is the bulk of my content, I think. So let's see, prototyping, risk reduction testing, process creation is all part of the create process. So you need to convince yourself that things will work and not think that you can just create one and done. Having a prototype helps a lot so that you can find your issues early. And then testing and improving the product. So something that you don't really think about until you get into the world of large complex products is how many requirements there often are. So you'll have a huge list of different requirements to test against, and you'll run many tests and make sure everything works exactly as you want. So you have to be kind of methodical about that. And then finally, there's delivery to the customer and even support and maintenance into the future. So any questions on this or anything specifically on the design process, how this can be implemented? I don't know if there is anybody looking at projects, engineering type projects for their students and thinking about, okay, how do we make this fit within a school year? Or I don't really know what your particular applications are. So I'm just kind of, yeah.
No questions, but I really liked your industry examples of the pieces.
Thanks.
They're actually very helpful.
Yeah, so I'm part of I just graduated from this leadership development program here at Lockheed, where we actually sort of go through all of these particular items in detail and practice with them and with mock customers. And so we get a really good understanding of each step of this process. So it's kind of just an essential skill as you go into industry to understand each one of these. So one of my last slides here is just some general inspiration. So what often inspired me I guess in high school, college, and before was real projects with that build and test phase. That's when all the fun happens, when you're actually testing out your product, you're testing out your little project and seeing it work. So bottle rockets, we had a custom bottle rocket design challenge in physics class in high school, and that was really fun. There's a goal in mind. We're actually putting a lot of effort into it, and everybody was exceptionally engaged. So that was really fun. In high school, on the bottom right here is a first robotics. So, I don't know if you have first robotics available at your schools, but if you do, I highly encourage you to get involved. It's really fun, getting to know your students as well, and seeing them extremely motivated to have their little robot work and do all these cool things. So upper right is or not the upper right, but the middle right is I think that's SE Formula Racing, which is a college competition. Very involved, but again, more valuable probably than any of the studies that you do in college for getting prepared for the real world and having those skills you need to be a real engineer. So, and yeah, upper right is just finally a product that you might make one day, real airplane. That's just a slightly bigger version of all of these things that you make down on the right. So, so yeah, you can kind of see the progression. And you probably already know this, but in terms of introducing science and engineering skills, so below high school, you could kind of do these same projects if it was below high school or at high school level. Some of them, but the concepts that are taught are probably just a little bit more in depth in high school. Well, a lot more in depth. So basic concepts like friction, energy, forces, or how different materials behave is like some good basic concepts below high school that can come out of these projects. And in high school, I know I took physics, and then I did AP physics. So we learned about kinematics and energy, and we did calculations to estimate how high a rocket could go, how far a marble could go on a roller based on its initial height, stuff like that, or even maybe how far a mousetrap car could go based on its potential energy in the spring. So when those engineering skills are connected to the actual project, then that's where I think the real engineering happens and the learning happens. So, but I also liked growing up field trips, actually seeing things, demonstrations, science museums, rocket launches. If you live near a launch pad, airports, just checking out planes and kind of learning about it and studying them, and or even factories, if you could go to like the Boeing factory or something, and just learn from folks there. It's very valuable. So that's all I have for my bulk of my slides. This is really just a demonstration for what we do at the STEM Council in Lockheed Martin Acolyte at our site. So we do outreach based around optical engineering. So this is usually trying to teach students about basic optical physics, right? So how do light rays react? They can reflect or go through materials. How do they change their direction? All of that really matters for lasers because it determines where the laser goes. So we have to have a very good understanding of that. So we try to communicate this. Some things we do are lenses, mirrors, lenses, and teaching about the basic concepts like Snell's law of refraction here. So, and then once we teach them a little bit about the basic concepts, we have a hands-on activity. What we were able to do over the last year is virtually we're able to use this optics simulator online. It's a free online tool where you can place light sources and then have optics redirect that light and create a pattern or move that beam where you want it to go, which is very similar to what we do here when it comes to laying out layouts for layers for lasers. So here's some example activities from that, replicating a eyeball. And this is, I think, collimating a lens, collimating the light source here, and the telescope. And on the upper left, the solar collector. So that's pretty cool. So just a short example of how the solar energy trough works here. The sun is a point source, and then this big concave mirror concentrates it down, and that in real life makes it focus onto this little tube here, which has the working fluid in it. So it's nice to be able to show how this little simulator is, it's nice to be able to replicate the real world application so simply and easily, and get that understanding that the physics of it aren't really that hard. The implementation might be harder. So, and then just a little bit more detail about how these different applications work. So not totally relevant to our discussion, but good examples for the activity to sort of just challenge the students a little bit about this concept and hopefully have them learn a little bit more. So yeah, that's it. is there any questions?
There are questions. So also thank you so much for sharing about the virtual activities. I think that's super cool. I remember in my physics classes, things around optics and like waves were really hard to, to study and to like learn about, because in some ways it's much easier if you can see them actually happening in front of you. So that's super, super exciting. And yeah, and I, from my end, sending it out to all sorts of people to try to see if we can get some people engaged and interested in this, because I think it's awesome. Okay, so for some questions, so, and this is, I mean, I can vouch for also hearing this in terms of mechanical engineering. For students who kind of, I guess, would assume that like mechanical engineering isn't, just computer stuff. I guess, like, is there anything, that we can share with them that's encouraging in terms of, it's there is some, just, obviously a fair amount of computer work, but there are, some other, I guess, if you're just going to be interested in to know if there's, what are other cool stuff that you do that's, even if it's on the computer, but just it's not just CAD all day.
Well, I guess I touched a little bit on actually assembling parts. So the most satisfying part of the job is after you design the thing and then you had the thing built, and then it's in your hands in the lab. So not everybody gets to see everything, but everybody, I think, has the opportunity to go see the thing that they designed eventually. Depending on the company or the program that you work for, it could be a lot longer until you see that thing that you designed. So if you really want instant gratification, you could work on a program where you're doing a lot of little prototype work, or you need to make little things all the time. So, but it's also extremely encouraging when you have like a giant rib of an airplane wing that you designed and it's so beautiful, you spent so much time on. That's also really satisfying. So, so yeah, I mean, in terms of computer work, yeah, there's a lot of the CAD. It's way better to do it on the computer than drawing. I mean, you're not breaking your back, so you just can be happy about that. When you're if you're ever feeling bored that you're sitting computer too much doing CAD, but I mean, it's almost like a video game, so it's not bad. You're kind of spinning the thing around on your screen, and that's satisfying. You can make it pretty colors. So and then if you're, it's a little bit of everything, and it's an extremely broad field, and that's why I wanted to go into it, because you have a lot of opportunity as mechanical. You can do more just coding and really like physics oriented mechanical engineering, because you're different than a physicist in that you're really focused on the application. So so it's I guess that's a type of job that you are still very valuable in, doing analysis work of heat transfer and all that stuff, and all that you'll learn in college as well. Being able to do analysis of structures and heat flow. So, and that can be an interesting academic exercise where you sit down and you actually just like writing out and trying to figure out the problem on paper. How exactly does this physics work? So that's different than the computer work. And then obviously being hands-on is the most fun, but or seeing the actual thing operate and work well, that's obviously the most satisfying. Yeah.
No, thank you, because I do think, certainly, the idea that you can see it at some point, and that it's a thing that you actually designed, I would imagine would be, encouraging to students who are, it's like, oh, sounds like a lot of computer stuff and really boring.
Yeah, I mean, I have a short attention span also sometimes, so like that's also why mechanical engineering, I'm like, oh, things that move, it's fun. Yeah. So I like to be able to get up occasionally and just play with hardware, because
Yes, that sounds pretty. I mean, I guess we want to work on some stereotypes. Just being able to manipulate things with engineers. And I guess, okay, so another question we have is, what would you say is your favorite part of your job?
Mm. Mm. That's tough. There are a couple favorites. Uh, hmm. My first favorite is when I get on a groove in design and I start designing one thing and then the next thing, and then I I just everything starts fitting together, and you're forming a sort of masterpiece in your own way. Um, I guess in any job, you can, if you like it enough, you might consider it like an art. If you're really good at coding, you might create, really beautiful code that's elegant, and you might just become sort of attached to it. So in terms of coding or designing mechanical parts, when things are working really elegantly together as you wanted, that's extremely satisfying, and you feel like, wow, I accomplished so much today. So that's probably the most satisfying, I guess. Or all right, I would say that's second most satisfying. Most satisfying is definitely when your customer tells you this looks great or this works great, and I get that occasionally because my customer sort of is often my lead, who is internal to my company. So I give him something like a tool, and we use it and it works great, and that's the most satisfying. We're like, oh, we need this guy to make more stuff for us, and that's definitely the most satisfying recognition, right? So, but yeah, that and having the time to sort of create everything perfectly as you want and have ownership over your work.
Awesome. Actually, so it's on the same vein. What's your least favorite part of your job?
Probably making people do things who don't want to do things. Delegating work, that's not easy. Obviously, it's always easiest to do your own work, but sometimes you can't do everything, and that's a really hard thing to get over. There's a lot of people who just try to do everything themselves and are very stressed out, and it's not good. But you have to be part of a team, and if you invest enough time in your team, then generally you can have a good enough team that you can work like a well-oiled watch. So.
Well, and then how many people are on your team? How many people do you work with on your team?
I probably work with about 5 people regularly. My whole site here has like 190 people or so. But actually in the office these days, there's a lot less people. So it's like maybe 5 to 10 people that I work with regularly. And stop by their desks, look at some designs together, brainstorm how to solve a problem, and somewhat normal still. So
yeah, I've been back at the office, and people are slowly trickling back in, and I gotta say it's really weird to see other people in this building.
Yeah, it's like, who are you? I don't it's funny, but I've been here for the last year, so in the office.
Yeah, no, or see, people I've accidentally surprised people a little bit, and they jump because they're like, oh, I was not expecting another human being literally in this building today. And I was like, oh, I wasn't either. So I kind of jumped too.
Right.
And let me see if you have any more questions. And actually one more question, and then we can wrap up. So I know with mechanical engineering, there's as far as I understand it, there's a couple there's sort of, and you alluded to this, as like, different directions you can go in with like mechanical engineering. If you like thinking back on sort of your own career, are there any other like sort of like niches or like, kind of more specific areas of mechanical engineering that you think are super cool or wish you had gone into?
Yeah, so that's a good point. I'll expand a little bit on that too. So I think it's somewhat important to get very familiar with a certain type of technology that makes you very strong in that field. So you could become very good at energy systems. You could become very good at space. Then you'll be very employable at different space companies. There's a lot of I'm always surprised by how enthusiastic space people are.
Oh, they are so enthusiastic. Okay, I'm glad I'm not the only person who's ever noticed that.
Yeah, so space people are always really excited. It's very cool. So you can, once you develop a good baseline knowledge of that, it really helps you to connect with other space people and getting a job or even moving within a company is easier because you know about the technology and you can transition more easily. You have a better jumping off point. People think that you have a better idea of what you're doing, and you probably do. Yeah, so there's a lot of emergent technologies, and I think it's reasonably smart to sort of grab onto one. You have a good baseline knowledge and experience of a lot of different things, and then grab onto one and sort of specialize, know a lot about like a certain technology that I guess works with your lifestyle. Like, I want to work in space. I want to live in these different places where there's a lot of jobs for space people, and so in the end, that'll work for my lifestyle. So yeah. Let's see. Energy, space, yeah, automotive. Those are just some examples. Yeah.
Awesome, thank you. Thank you so much for presenting, Andrew.